Yeah, so we in lab, we did this in lab and lecture, right? So remember that this is a little different than what a cardiac myocyte, individual cardiac contractile cell looks like, which remember it comes up, plateaus, goes down. This is the entire electrical activity of the entire heart, all at once, sends through your skin, right? We put electrodes on your skin. And you have, for us, three major waves. The P wave, which is atrial depolarization, right? And then you'll have a segment here called the PR segment, which is basically the part of the EKG that's flat between the P and then the Q or S wave, which is the most complicated wave, the tallest wave, which is ventricular depolarization. And then you got an ST wave, and then you got the T wave, right, which is ventricular repolarization, right? Now, atrial repolarization happens in the middle of the QRS, like we talked about, and you can't see it. Now, in lab, you reverse the electrodes, and then your QRS turned the opposite way, right? And if you put the electrodes normal and that's happening, then there's something going on in the heart, right? You saw that on my EKG. I had a couple that were going the wrong way, right? Which means the electrical activity has either been reversed or during cardiac arrest, which is what they were worried about the first time they found that online. That happens, where the QRS is actually reversed, where it shouldn't be, or it's not even there. And that's because the heart cells at that point are undergoing severe stress, and the electrical cells aren't producing the proper electrical output that they normally would, right? And of course, if you have an elevated T wave or a flat T wave, or you have a prolonged PR segment or PR interval, those things can tell a clinician that you might have something going on in the heart, right? And they would have to do other tests, because this is only the electrical activity of the heart, nothing to do with the mechanical activity parts of the cardiac cycle, which is what we're going to do today. So, and you guys got to do a little of that, playing around with, evaluating EKGs. The first thing a clinician typically does is just look for all three waves, right? And through consecutive heartbeats, and then they can start measuring segments. They can get heart rates. They can look at the waves and make sure they're, with normal shape, normal height, those kinds of things. And they're really good at doing that really quickly. So I put this after we get through all the electrical activity, because we have really stuck with looking at our cardiac muscle, right? So when we do muscle tissue later, we'll just do skeletal and smooth, because we've kind of already got this all set up, right? And we've already went through all of it. So the two that you're really going to pay attention to for this exam are being able to compare and contrast contractile versus autorhythmic cells, and that kind of summarizes the major differences and similarities between them that we did in the lecture. Then we'll come back to skeletal muscle and talk about it. And it behaves a lot like a contractile myocardiocite. The major difference is that these cells are voluntarily controlled and they won't contract. I mean, you don't want skeletal muscle contracting when it's not supposed to, right? You don't want to punch yourself in the face when you're just sitting there. And so you want to have control over your skeletal muscle, which is controlled voluntarily by parts of the brain, parts of the cerebellum. So that allows us to talk a little bit about the mechanical events of the heart, what the heart does, right? We know the heart produces blood pressure, so it squeezes on the blood. That produces hydrostatic pressure, because the majority of the blood, and we're going to go through blood composition also, is water, right? Or at least 50% of it is water. And so we squeeze on that fluid, that produces hydrostatic pressure, blood pressure, and that's what forces blood through our closed circulatory system. And I put a mammal heart up here. I'll also show you, a different extreme. I'll show you a fish heart here in a little while, so you can see the differences between kind of what we would consider an ancestral or basal heart or a simpler heart. compared to obviously the most derived heart here, which is what all mammal hearts look like. When you look at a mammal heart, there are 4 chambers. Really, the mammal heart is 2 separate pumps. It's a right pump and a left pump that's separated completely. Because of that, blood on the right side and blood on the left side will never have the ability to mix, right? They're not going to mix, which is important because the right side of the heart is going to receive deoxygenated blood that's returned from the body. And the left side of the heart is going to receive oxygenated blood and send it out to the body. And so you don't want deoxygenated and oxygenated bloods mixing because that would make it less effective, right? Delivering oxygen to tissues. And that's really incredible in mammals because mammals have such high metabolic rate, right? We're warm-blooded. We need really good and efficient oxygen delivery. And really, a lot of our tissues and our bodies do not tolerate low oxygen levels. It's just that we're such strict regulators that our cells have evolved to be happy, right? To have a lot of oxygen. And if you deprive them of oxygen, they don't do so well. So this traces blood flow, typical blood flow, through a mammal heart, right? So we have 2 upper chambers, the atria, or atrium is singular here. We have 2 ventricles, and we have valves that separate the ventricles. The valve on the right side has 3 cusps, and it's called the tricuspid valve. Right? Cusp means flaps, so 3 flaps. The left side has 2 valves, or 2 flaps to their valve, and that is called the bicuspid valve, or it's sometimes called the mitral valve because when it's closed, it looks like the mitre hat on top of a pope or a bishop in the Catholic Church. The reason there are differences here, there are 2 flaps on the left side because the left side produces a lot more pressure. And so keeping 2 flaps closed is a lot easier than keeping 3 flaps closed, right? If you have a lot of pressure. But mitral valve prolapse, for example, in humans is pretty common, believe it or not. I've seen research papers that suggest maybe 40, even 45% of the population has a little bit of blood that leaks from the ventricle back into the left atrium. Now, some people have really leaky valves and they have to be fixed. The valves, what they keep blood moving in one direction. We don't want blood that left the left atrium to the ventricle to go back into the atrium, right? We want it to go up into the aorta, and so we don't want leaking. You can hear that leaking if somebody listens to your heart during the sounds, particularly ventricular systole or contraction. You'll hear a hissing sound when you're listening. You can be able to hear the blood leak. But if we we'll just start on the right side. The right side is going to receive all of the blood coming back through the veins, through venous circulation. And in a mammal, there are 2 huge veins. The 2 largest veins in the body are what are called vena cavas. There's a superior vena cava, or a cranial vena cava, and an inferior or a caudal vena cava. And the cranial vena cava on top drains everything above the heart, and the inferior or the caudal vena cava drains everything below the heart. And all that blood returning from all of those tissues is going to be deoxygenated because it spent time in the tissues and dropped off oxygen and picked up carbon dioxide. And that deoxygenated blood, you can see in blue, comes into the right atrium. After filling is complete of the right atrium contracts and forces blood through the tricuspid valve into the right ventricle. The right ventricle will then squeeze blood up into what's called the pulmonary trunk, which will branch into left and right pulmonary arteries. Remember, arteries take blood away from the heart. And that deoxygenated blood is going to travel to the lungs, where it picks up oxygen, drops off carbon dioxide. The reoxygenated blood will then return through pulmonary veins to the left atrium, which is going to receive oxygenated blood from the lungs. The left atrium contracts, will push open the bicuspid valves and fill the left ventricle. the left ventricle then will contract and force blood up into the aorta. Now, the pulmonary trunk and the aorta also have valves. Right? There's a aortic semilunar valve and a pulmonary semilunar valve. And again, you can imagine when the ventricles contract, they contract, remember, from the bottom up, and they're going to force blood up. And as they come up, it's going to close, right, the valves. And then as pressure builds, then the blood is going to take whatever the least amount of resistance or outlet, and that's going to be through the pulmonary trunk and the aortic trunk. And so enough pressure has to build up to pop open those semilunar valves, and that will eject. It's called ventricular injection. It will eject blood into the aorta and into the pulmonary arteries. Now, as the ventricles then relax, you can imagine that pressure drops, right? And then gravity is going to pull blood down, right? And as it pulls down, it's going to close the semilunar valves, preventing that blood from leaking back into the ventricles. So again, it just keeps things moving in one direction. And that's kind of blood flow through, right? And as blood leaves the aorta, it will then be delivered to all of the major systemic arteries, which branch into smaller and smaller arteries, delivering blood to capillary beds, right? Everywhere in the body. We call that systemic circulation. That deoxygenated blood, or the oxygenated blood will then drop off oxygen and collect carbon dioxide from cells in the tissues of the body, and then veins will recollect it, right, and re-deliver it back to the right side of the heart. So the vena cavas are the largest veins, the aorta is the largest artery, and then the pulmonary arteries and veins connect the heart to the lungs in mammals. So that's kind of, at least understanding blood flow. Now, what we'll do is we'll go through a single heartbeat here in a second, so that you can see, how much blood's ejected and what happens through an entire single heartbeat or one turn of the cardiac cycle, is what we call it. So this is just a dissection picture of a mammal heart. For my eyes, I can see it better. So you can see the valves here, right? And when you look at the ventricles, you can tell that the right side of the heart, the wall of the heart, is less thick than the left side. See how thick the ventricle is? So what you're going to learn, and what I'm going to teach you, is that the ventricles eject the same amount of blood, which makes sense because you want both pumps, since they are kind of separate pumps, to be ejecting the same amount of blood, right? So that everything's running through the system evenly, if you will, right? That is, you don't want less blood going to the lungs than it's going to the body, right? You want even amounts. The big difference between the two is the amount of pressure. So 120 millimeters of mercury are being produced by the left side of the heart. Tremendous pressure, right? Whereas on the right side, it might be like 20 or 40, 50 millimeters of mercury. It's a lot less. So it's like a super soaker versus a regular squirt gun, right? You're still sending out the same amount of fluid. You're just doing it at a much different rate of speed and pressure. Does that make sense? The atria on top are really thin because all they're going to do is push blood into the ventricles. Right? That's all they're doing. So they have really thin walls. This is your septum here that separates the two. And I love this photo. What they did is they stuck a flashlight behind one of the flaps of the tricuspid valve. And you can see that the valve itself is actually anchored into place by these really thick, strong, dense, irregular connective tissue ligaments. And these ligaments are called chordae tendineae. And what they do is anchor the flap, but when the flap's open, the cords are actually slack, right? So they're like rope. Think of rope, loose rope, and as blood is filling the ventricles. Then as the ventricles contract and push the valves close, the cords become taut, right? They become tight. And then there are little muscles they're attached to, and they're kind of hard to see down here. But you see these little bubbles of muscle right here? Those are called papillae, right? Or papillary muscle. And the cords are attached into those. And they're like almost separate little muscular units. And as the valves close, the valves are going to want to do this. They're going to want to pop up, right, into the atrium. Well, we don't want that to happen. So at the same time the ventricles are contracting at their maximum force, the cords are then pulled by those papillary muscles to prevent them from popping open. So they're pulled down during the maximum pressure produced by the ventricles to prevent the flaps from popping into the atria. So we don't have blood moving back into the atria, right? We want it to move into the aorta and the pulmonary trunk. That's kind of what the chordae tendineae do and how the valves work. So you can see here as the valves close, the blood's going to swirl underneath, and these papillary muscles will pull down to make sure the flaps don't open back up. And that's called prolapse when they do open back into the atria. As blood swirls under the valves, that's what produces the heart sounds. So when you're listening to somebody's heart, looked up, that sound is from swirling blood. The friction, well, I guess it's just the sound of blood that comes from it swirling. The first sound is closing of the atrioventricular valves, both of them, bicuspid, tricuspid. And the second sound is blood swirling when the semilunar valves close during ventricular relaxation. I'll show you where they happen in the cardiac cycle here in a second. That's kind of how the valves work and the muscle, differences between the right and left side of the heart. So I kind of walked you through blood flow, right, before with the heart, and then I threw this slide in just so that you can follow it, right? And I like to ask a question often about, trace blood through the heart starting in the left ventricle. And come back to the left ventricle as one of your little short answer questions, right? You can fill out the steps. And so this is basically the flow through all of the chambers of the heart in a mammal. All right, so here is your mechanical events of a single cardiac contractile cycle or a single heartbeat. This happens with each heartbeat. And typically, there's a bunch of information on here. Here are your sounds. Here's sound 2 and here's sound 1 of the heartbeat. And then we got these two terms, diastole and systole, right? So what are those terms? So diastole means relaxation. Systole means contraction. So you can have atrial systole, or you can have ventricular systole, right? So atrium and ventricles are obviously going to contract at different times, right? If they contract at the same time, what's going to happen in the heart? So if your atrium and ventricles contract at the same time, blood's going to go where? Nowhere, really. Right? You probably just kind of. It might eject a little bit, but it's just going to kind of slam into each other, right? So we want the atria to completely contract and relax before the ventricles start, right? So they're going to kind of contract at slightly different times. Remember, the SA node, when it fires, that causes atrial contraction. We also communicate that electrical signal to the AV valve, or AV node, right? But the AV node delays. Remember that AV node delay before it fires, which allows the atria to completely contract and relax before the ventricles actually start contracting. So let's start. We'll start up here. We'll just follow the numbers. So number 1 is called late diastole. And during late diastole, all the chambers of the heart are relaxed. All right, so atria and ventricles. And at this point, we just finished a complete heart cycle of beats, and now everything's relaxing because the atria were already relaxed and the ventricles are now relaxing. And the pressure is dropping in both. So, have you all had physics? Everybody had physics? No? All right, so volume. If volume increases, pressure drops. If volume decreases, pressure increases. Okay? So just think of any chambers that is that way. So if you increase the volume, you're dropping pressure. If you decrease the volume, you increase pressure, right? And you think about that. If you take a balloon and you fill it, right, or you expand it, the pressure drops, so water will go into it. You squeeze on the balloon and decrease the volume, and the water squirts out, right? And the pressure increases. So because all of the chambers are relaxed here and they're all kind of at maximum volume, then all the pressure is low in the heart compared to the blood vessels that connect to it, right? And so blood is going to fill. So filling is going to happen. And we got what's called passive filling here because nobody's contracting. It's just differences in pressure. So blood's coming in from the veins, right, into the left atrium. Blood's coming in through the pulmonary veins into the right side. And then enough blood builds up in here that it just simply opens the valves. Gravity, it's just like putting fluid on top of the valves, they open. And then the blood starts filling the ventricles. And all of that's happening passively at the beginning of a heartbeat. Now, eventually, we know the SA node depolarizes, right? It does this. It depolarizes automatically. It does it about 60 to 80 times a minute. And when it depolarizes, that'll spread through the atria, and then you'll get what's called atrial systole. And at that point, you're just going to push the blood that's in the atria, the rest of it, right, into the ventricles. That is, pressure is going to build up here. You're going to stop passively filling, and you're going to just eject whatever's there, right? Whatever's left over, whatever hasn't passed into the ventricles. The valves are already open, so we eject the blood from whatever's in the atria into the ventricles during atrial systole, and then they start to relax. Right? By that time, then we would have passed our electrical signal to the AV valve, and it would have, to the AV, I don't know why I want to call it a valve today, to the AV node. And the AV node will then send the electrical signal down those bundle branches, right? Down the septum and all the way down to the apex. And then what will happen is the apex will start contracting, right? And as the ventricle contracts, it's going to push blood up. Now, at the end of atrial systole, or the ejection of blood from the atria, you have an end diastolic volume, right? And this is called end diastolic volume because it is the end of diastole for the ventricles, okay? So end diastolic volume, or the amount of blood found in the ventricles before the ventricles contract in a human, or typically a mammal about our size, in a human, but these are human numbers. It's about 135 mils of blood. Right? So your ventricles hold about 135 mils of blood before the ventricles start contracting. Now, as the ventricles contract, they're going to push the blood up, right? And as they push the blood up during the start of ventricular systole, then the valves close. And at that point, no blood is moving anywhere, right? Because you have just enough pressure built up to close all the valves. All 4 valves are closed, both atrioventricular valves and both semilunar valves. And so no blood is moving, and that is called isovolumetric ventricular contraction because no blood is moving anywhere at that point, even though contraction is happening. Eventually, the pressure builds up enough that you pop open the pulmonary semilunar valve and the aortic semilunar valve, right? And then you get ventricular ejection. You eject blood. And so ventricular systole has isovolumetric contraction and then ventricular ejection. And then once you're done with ventricular systole, the ventricles start to relax again. You ejected a certain volume of blood. You can't eject all of it. It's just impossible to eject all 135 mils. And so notice your end systolic volume at the end of ventricular systole is 65 mils. So you eject, 70 mils of blood, something, right? Around 70, 80 mils, depending on the person, or ejected. Now, what does that mean? That means the right side ejects 80 and the left side ejects 80, right? Remember, they eject the same amount of blood for the most part. They just do it at different pressures. Now, right at the end of systole of the ventricles, think about this, your AV valves are closed, right? Because of ventricular contraction. And your semilunar valves were just open, weren't they? Because we ejected. They close. And then the blood in the pulmonary trunk and the aorta close the valves and swirl, giving you your second sound, right? At the swirling here. And their first sound happened when, right here at this point, when you have isovolumetric ventricular contraction. So you've got all the valves closed here. That's just like right here, isn't it? But now it's not during systole, it's during relaxation, right? Or diastole. So we call it isovolumetric ventricular relaxation, or some of the times it's called isovolumetric ventricular diastole. Over here, this is often called volumetric ventricular systole. And so you got contraction where nothing's happening, no volume's moving, and you got relaxation where no volume is changing in any of the chambers. And then as you move back to number one, then all of a sudden you get filling, right? And as you fill, then these valves are going to open because the blood on top gets heavy, they open and they start filling the ventricles. So isovolumetric ventricular relaxation is going to be completed once the atrioventricular valves open with atrial filling, and they start to fill the ventricles again passively. And then we start all over again. We get an SA firing, right? Atria contract, and then relax in diastolic volume, and we start over again. So that happens all with each beat of the heart. So with each beat, we're injecting a certain volume of blood, and we're going to give a name to that volume of blood that's being injected. It's called stroke volume, okay? Because every stroke of the heart injects a certain volume, right? So we call that stroke volume, and stroke volume is somewhere around 70 mils, right? 70 to 80 mils of blood are injected with each heartbeat. Questions? Okay, so that volume that's ejected there at the end, what we call end systolic volume, the volume that's ejected is about 60 to 70, 60 to 80 mils. That's called stroke volume. The heart, therefore, is about anywhere from 60 to 70% efficient in ejecting blood into the pulmonary and systemic circuits. Interestingly, there's an intrinsic mechanism built into heart muscle that's called the Frank-Starling mechanism. These are two physiologists that were studying the heart. And they noticed that if you get increased stretch of the heart at any time during the cardiac cycle, you can get harder contraction. And I'll give you an example. When you're sitting here relaxing during lecture for an hour, you're sitting in stasis, right? Your heart's beating at a certain rhythm. And the contraction, or how hard the heart is pumping blood, is pretty consistent with each heartbeat. If you get up and start walking out of the room, what's going to happen is you get up and your legs contract and you start walking forward. That forces more blood back into the heart because all that blood in the veins is going to be squeezed up really quickly into the heart. And so all of a sudden your atria receive a larger volume of blood than the last hour, right, that you were sitting at the table. And that extra stretch of the atria immediately contracts harder, right? So stretch of heart muscle causes harder contraction. And so the greater the venous return, the harder the atria and ventricles contract, which is pretty cool because your nervous system or your body doesn't have to do anything. You get up and start moving around, your heart starts contracting harder. Not necessarily faster right away, but harder to deal with that volume of blood that is coming back to the heart. And then you can remove that volume back out again, which will supply the skeletal muscle that's not working, correct? And if need be, and if your muscle is not getting enough blood, then you can actually increase heart rate if you have to. So that intrinsic mechanism is just built into cardiac muscle. It's built into cardiac muscle. Now, there's a reason for this. In skeletal muscle, when I'm relaxed, and if I'm just thinking of the triceps muscle, or biceps here, biceps or triceps. When I'm sitting here, and when I move my arm up, when I move at the elbow, I'm contracting biceps, right? When I'm relaxed, biceps is at the perfect length to get maximum contraction. That is, remember your sarcomere that I showed you a picture of, the actin and myosin overlap, is maximum overlap that allow complete shortening of what we call a sarcomere. So sarcomere length is optimal. Sarcomere length is optimal in a skeletal muscle. In the heart's very flexible. So if there's not a lot of blood in it, the sarcomere length is going to be very small. If it's got a lot of blood in it, or you add a little bit, it's going to get longer. A little more, it gets longer. You're increasing the length of the sarcomere because cardiac muscle or any muscle tissue is elastic. Right? So you have, in the beginning, with very little blood, you have poor sarcomere length, so the contraction power of the heart's not very strong. But the more you stretch it, the more you fill it, that is, before each contraction, the harder the contraction, because the better or more optimal the sarcomere length is. Does that make sense? We can actually try this. I'll find some weights, and we'll do this with the gastrocnemius muscle in the frog. We'll actually cut the gastrocnemius muscle, and what it'll immediately do is it's like a rubber band. It'll get really short. Then we'll add some weight, and we'll stretch it slowly, and we'll see contraction gets harder and harder and harder and harder. Okay? Now, you can imagine the biggest problem is what happens if I stretch the sarcomere too much? This is actin, this is myosin, right? If I stretch it too much, you're not going to get any contraction because there's no actin-myosin interaction, right? So we prevent that in the body with skeletal muscle, right? What happens if you hyperextend? Does your body tell you about it? It doesn't feel good, right? So you stop. Hopefully you stop. Your heart has a connective tissue sac around it called the pericardium. The pericardium is inelastic. What that means is it doesn't stretch. So the heart can only stretch as wide as the pericardial sac is, which prevents too much stretch for the heart itself. And so, you have to prevent those sarcomeres from becoming too stretched, or then you don't have actin and myosin overlap. Does that make sense? So the more you fill the hearts, the larger the stroke volume. So instead of ejecting 60 mils, you might eject 80 mils when you get up and start moving around. This is built into people who are like to do cardiovascular exercise, right? Marathon runners have very low heart rates, right? Somebody that sits on a couch and does nothing has a much higher heart rate. Why? The reason they have a lower heart rate is because they're training a muscle. They run 8 miles a day or whatever it is. If you're a distance athlete, then their muscle, the heart itself, responds by lowering heart rate, which allows more filling, and they're ejecting more blood per heartbeat than somebody that doesn't exercise. Now that doesn't mean they're moving more blood per minute than somebody that sits on the couch that doesn't do anything. They're just moving blood more effectively, right? So they move the same amount, but they do it with lower heart rate, and which allows for more stretch and harder contraction. So their stroke volume is much more elite, if you will, or higher than somebody that isn't a marathon runner, right? That's why marathon runners can have heart rates of 44 beats or 45 beats per minute, because they have very efficient hearts with very high stroke volume. It would be double that, if that makes sense. And that's all because of how the Frank-Starling mechanism works. Now, what cardiac output is, so stroke volume is the amount of blood per beat, right? Cardiac volume is stroke volume times heart rate. It's the amount of blood ejected per minute, right? So, for example, if you have a heart rate of 80 beats per minute, and you eject 60 mils, you multiply those two together, right? And that'll give you outputs of your hearts per minute at rest, which is what, 4,000 mil, 4,800 mils, right? Or something like that. It was 60 times 40, right? Is that great? Did I do the math right? Yeah, 4,800. I think so. So that's 4.8 liters per minute, right? Or maybe a little higher than that if you have a little higher heart rate. That's about the volume of blood that's in your body, which is pretty cool. At rest, you move, your heart's insufficient. You move the whole volume or almost the whole volume of blood through the whole cardiovascular system in 1 minute. Now you can double, triple this, quadruple it by exercising, right? Or you get up and start moving, your heart can contract harder, and your heart rate can go up, and you can speed this up, right? And move a lot more blood to get a lot of oxygenated blood going to the tissues that are metabolizing it. That's not particularly skeletal muscle. Now, many factors can alter cardiac output. So intrinsic factors like this, right? The nervous system. Somebody comes up and grabs you, your heart starts beating harder and faster, right? And the endocrine system, right? Can release hormones that tell the heart to speed up or slow down. So, well, let's talk about a few of those. This is I threw this figure in here. Exercise and cardiac outputs. Everybody should do some cardiovascular exercise. Now, would you have to go run? No, you just walk. Walking's great. Walking's great. Walking on an incline is fantastic. So my wife can't run anymore. She used to be a marathon runner. Oh my God, that's insane. Her knees are bad. So she walks with one of those weight vests now on an incline. And her heart rate gets into the 140s. And she's not walking fast. She's walking on an incline with weights to work her heart. You need to work your heart. It's a muscle like any other thing. And if you do that, you're going to increase the efficiency of the heart by slowing heart rate and allowing for more stretch. That's how the heart responds. And so if you look at this, this is kind of what I was mentioning before. Cardiac outputs of somebody that does nothing versus somebody that exercises is exactly the same, right? It's about 5.25 liters per minute, or about the amount of blood that's in your body. The difference is their stroke volume, 70 versus 120, right? See that? So they're injecting a lot more blood per beat because their heart rate is much lower, which allows for more stretch before contraction, right? More stretch, harder contraction, bigger the stroke volume. Now, what does this mean? If this person chases that person down the streets, their heart rate's going to go up really fast. And when your heart rate goes up really fast, it becomes inefficient. You get really tired really quickly, and you got to bend over and breathe or fall on the ground. Where this person just keeps running, right? So their heart rate doesn't go up. This is heart rate double from rest. That's kind of how it works. So that's how exercise affects the heart. So this Starling law that I talked about, this stretch before contraction, is called preload. Right? So think about you're stretching something before you actually activate it. Right? And then the more stretch you have, the more effective that contraction or shortening. And that's called preload. That's the degree in which cardiac muscle cells stretch before each beat. So obviously, if you allow for a longer filling time, you get more preload and a harder contraction, right? And then a larger stroke volume. Now, what the preload and contraction is overcoming is what's called afterload. Afterload is the pressure in the blood vessels, right? So have you guys ever heard that high blood pressure is the silent killer? That's what they call it, because a lot of people with high blood pressure, but not too high, not like really, really high where you get headaches and you feel really bad. If you have high blood pressure for 25 years, what are you doing? With every heartbeat, it gets harder and harder to push that blood into circulation because there's more pressure than normal pushing against the heart, right? So this is why it's important to get that 120 number closer below 120. A lot of high blood pressure is genetic. I have high blood pressure. It's a pain in the ass. I exercise. I eat right. It's just genetic. So I have to take blood pressure medicine. Plus, my heart's weird anyway, so they got me on the beta blocker anyway. Right? And it's annoying to have to do that, but you want to keep your blood, blood pressure low because it damages blood vessels and it also makes the heart work really hard. And eventually, what happens is you get congestive heart failure. Remember I mentioned that, where the heart is any muscle. Eventually, if you are overworking it, it's going to get bigger and it's going to get worn out, right? And so it starts failing after 20 years of high afterload. And then, it's going to lower lifespan. And you'll have to use drugs like the Foxglove we talked about that kind of will help with increasing contraction. So intrinsic factors that help increase stroke volume. One of the major ones is venous return, what we call returning blood from the veins back to the heart. Right? And one way we can do that is by simply contracting skeletal muscles. So I like to call skeletal muscles in our bodies skeletal pumps. They actually help the heart. They're kind of they're kind of a helper, if you will, a synonymous pump that kind of helps the heart do its work. And when you, like I was saying, when you get up and start walking out of this room, you start using your skeletal muscles. What's really cool are most veins and most lymphatic vessels are strategically placed between what are called opposing skeletal muscle groups. So, for example, the blood vessels that drain the legs are found between the hamstrings and the quads, so that when you move them, you're squeezing the vessel. And that helps fight gravity and push the blood up, right? So as you start moving around, your veins are strategically placed. That skeletal muscle can squeeze on them and force blood up or through the vessel. Veins, particularly the medium-sized, the small veins, also have valves, like the heart. And it'll become apparent why they have this when we start talking about veins versus arteries, because veins have very low blood pressure. And so if you compartmentalize or break the vein up into small compartments, then we can keep blood moving effectively in one direction. And it's not backing up and going and dropping and going, right? You're actually moving it from compartment to compartment. These valves are very common in the extremities, right? Because when you're sitting here, all the blood wants to pull into your feet, correct? And same with your arms. And so if I want to keep blood moving and not allow gravity to push it all the way back to my feet, I can use valves and skeletal muscle. This is why if you have to stand for long periods of time, you should move, right? My wife is a pharmacist. She stands for 10 hours to 12 hours a day. Have you ever tried to do that? It is. I don't do it, and it's really hard to do. She wears compression hose or compression socks to help return blood to her heart, or they get varicose veins, or they get damage to the veins and whatnot. Or her feet swell, right? Because she's on her feet a lot. So this is a cool picture up here. This is a picture of a vein in sagittal section showing you the two valves collapse that kind of compartmentalize that vein and help with blood flow. So venous return is really important. The larger the venous return, the more stretch, the greater the stroke volume. So you can do that with skeletal muscle, or you can do it, for example, with hormones if you really wanted to. Epinephrine can cause smooth muscle and in the blood vessels to also contract, and we'll talk about that here in a minute. Now, we know that the heart controls its own beats, its own rhythm, right? The SA node fires automatically. It does it 70, 80 times a minute to control our mechanical cardiac cycle and our heartbeat. But the nervous system can intervene. The nervous system can intervene when things are not going as planned, right? When you're not delivering blood fast enough, or you're delivering too much blood to an area. And the nervous system can come in and tell the heart to speed up or slow down. Now, the part of the nervous system that does this is called the autonomic nervous system, which is called the ANS, autonomic nervous system. There are two divisions to the autonomic nervous system. We'll talk again about these a little bit when we get to the nervous tissue. They're called the parasympathetic branch and the sympathetic branch, or division, if you will, of the autonomic nervous system. Both of these divisions send nerves to the heart, right? The parasympathetic nervous system sends nervous innervation to the heart via a nerve called the vagus nerve, which, if you take an anatomy, is an important nerve of the parasympathetic nervous system. 60% of parasympathetic output travels through the vagus nerve. So vagus nerve branches, which is cranial nerve 10, actually send a branch down to innervate the SA node, right? To innervate the SA and AD nodes. And the parasympathetic nervous system releases acetylcholine to these nodal cells, right, which control the rhythm of the heart. And what's going to happen on an EKG, it'll look like this. Notice your blips or your waves are very spread out, aren't they? Right? So you're going to slow heart rate, right? So the parasympathetic nervous system slows heart rate. The sympathetic nervous system is going to deliver its nerves through what are called cardiac accelerator nerves, right? And those cardiac accelerator nerves are going to, again, innervate the SA node and the AD node. And what they do is they release norepinephrine, which will do this to the EKG. You see your blips are closer together, so it's going to speed heart rate up. The other thing epinephrine does is it actually sends individual nerves to the contractile cells and can increase not only the speed of the heart rate, but it can also increase force of contraction. The parasympathetic nervous system does not decrease contraction. It only decreases heart rate. But the sympathetic nervous system, or epinephrine and norepinephrine, not only speed up the heart, but increase contraction of the heart. So you're not only increasing the speed at which the heart ejects blood, but you're also increasing how hard that blood is ejected. So that's where you get these two terms down here. Chronotropic versus ionotropic. Okay, so chronotropic is going to increase heart rate, all right? Or it's going to change heart rate. Chronotropic is going to change heart rate. So the parasympathetic and the sympathetic nervous systems are chronotropic to the heart. They either speed it up or slow it down. Ionotropic is only the sympathetic nervous system, which changes how hard or the force of contraction. So you can imagine, if you think about it, we talked about ions, right? Which ions are important here? And depolarizing and hyperpolarizing, right? So the chronotropic ions of importance here are going to be mostly potassium and sodium, right? The ionotropic is going to be calcium related, right? It's going to be calcium related because the more calcium you have, the harder contraction is, right? So how do these work? How do these work? So up here I found some pictures here for you. All right. Notice the parasympathetics over here, the mechanism with acetylcholine, and the sympathetics over here. Right. This is from your text that shows you how these two work. Now, acetylcholine binds to two types of receptors. One's called nicotine. You guys have all heard of nicotine, right? It's in cigarettes or tobacco or vapes nowadays. Right? Vapes, not cigarettes. Which is even worse on lung tissue. But what nicotine does is it binds to acetylcholine receptors and gives you all the effects of nicotine. There's another receptor that binds acetylcholine, and it's called muscarinic. Muscarinic are named for a toxin called muscarine, which is a toxin that's produced by mushrooms, believe it or not. So most mushrooms that you see out in the wild, you can't eat. You guys know that, right? They're poisonous, they call them poisonous. And they produce muscarinic. And so what muscarinic does is it binds to muscarinic acetylcholine receptors and shuts them down. So you can imagine why they're toxic, right? They affect the heart and also skeletal muscle. But the type of receptor that's found in the nodal cells, the SA node and the AV node, with acetylcholine, and the parasympathetic nervous system are muscarinic receptors. This is a G-coupled muscarinic receptor. Now, this is pretty cool in the sense that the G proteins in this instance don't cause the activation of kinases. They do, but they do it indirectly. They work directly on the receptors, which means when acetylcholine binds, the receptor changes shape, and we know we pop off GDP and add GTP, right? And instead of the alpha receptor turning on an enzyme, it actually goes directly to the channel and binds to the channel. When it binds to the channel, it changes the shape of the channel. Notice what it does. It opens potassium channels and closes T-type calcium channels. Remember, the T-type calcium channel is the last channel in the funny current that pushes at the threshold, right? So you're hyperpolarizing, allowing positive charge out, and you're preventing that last push, right, of the funny current to reach threshold. And so what's going to happen is with each of your contractions, your funny current's going to get longer and longer and longer, right? And so you're going to depolarize slower and your heart rate drops, right? What's going to happen with epinephrine and norepinephrine is the opposite of that. So, but notice we do have a kinase here. So now we are going to be a G-coupled receptor. This is the norepinephrine here. Epinephrine or norepinephrine will bind to two types of receptors. They're called alpha and beta receptors. And there are sub-alpha and beta receptors, like there's alpha 1, 2, beta 1, beta 2, found in different places. But here we have a beta receptor that binds norepinephrine or epinephrine. The difference, nora is released by a nerve, epinephrine is released by the endocrine system, right, by the adrenal glands, actually. But both of them can bind to the beta receptor. That'll change the shape of the beta receptor, activate our G-coupled receptor, release GDP, attach GTP, right? The alpha receptor will then cross and activate adenylate cyclase. So this is a G-coupled adenylate cyclase receptor. That produces CAMP, which turns on protein kinase A, and then protein kinase A will phosphorylate funny current sodium channels and T-type calcium channels. So now more ions are coming in. And so what happens over here is now your line gets steeper, right? So if you started out like this, and it'll start to get steeper, and then your heart rate will go up, right? Because you're depolarizing faster, right? So your funny current steepens, the slope does, with epinephrine, and it flattens with acetylcholine. I also threw this little table in here from your text that gives you the effects of each so that you can kind of have them right next to each other as you're filling out your review sheets, right? So that it kind of helps you to make sense of all of this. So it's cool because we've already learned all how those mechanisms, right? So we can kind of make sense how they work. The cardiovascular center in the brain that controls heart rate is found in the medulla oblongata, which is the top of the spinal cord. That's where those nerves actually leave. And then the lower parts of the brain, particularly the hypothalamus, are often in contact and control of what's happening in the blood and circulation, and then can control the activation of either parasympathetic and sympathetic, depending on what's going on in your body. All right, let's stop there. It's a good place to stop.